So far till now we have discussed Laguerre polynomials. Today we are going to discuss another important polynomial which is known as Associated Laguerre polynomials. Actually this Associated Laguerre polynomial is the solution of the Associated Laguerre differential equation. So first of all we will see what is the associated Laguerre differential equation, and then we will see what will be its solution. In fact, its solution will be associated Laguerre polynomial. So to know the associated Laguerre polynomials, let us start with the Laguerre differential equation for a positive integral n. And you know, for a positive integral n, Laguerre differential equation is this. This is x d2y dx square plus 1 minus x dy dx plus ny equal to 0. You know it. We have already discussed this equation in very detail and its solution too. As you know that Laguerre polynomials ln of x, these are the solution of this Laguerre differential equation, and you also know the solution of a differential equation always satisfy the differential equation. So definitely if ln of x are the solutions of this Laguerre differential equation, then definitely ln of x will satisfy this equation 1. So you can write this equation 1 in this way. This is x d2 ln of x dx square plus 1 minus x d ln of x dx plus n ln of x equal to 0. So this is the Laguerre differential equation. Now we will follow some mathematical steps to know what is the associated Laguerre differential equation. For this, let us differentiate this equation 2 by using Leibniz theorem m times. So differentiating equation 2 m times by Leibniz theorem. I hope you have studied Leibniz theorem in the course of calculus. So when we will differentiate this equation 2m times by Leibniz theorem, what will be the result you can easily see. So this will be x dm plus 2 dx m plus 2 ln of x plus mc1 dm plus 1 dx m plus 1 operated on ln of x, and plus 1 minus x dm plus 1 dx m plus 1 operated on ln of x, and plus mc1 dm dxm operated on ln of x times minus 1 plus n dm dx m ln of x equal to 0. And for this, definitely n should be greater or equal to m, because if n will be less than m, then all terms will be in fact 0. So n must be greater or equal to m. Now let us simplify this a little bit. You can see we can write x dm plus 2 dx m plus 2 operated on ln of x, and plus mc1. You know mc1 is what? This is m factorial over 1 factorial times m minus 1 factorial, and this is dm plus 1 dx m plus 1 operated on ln of x, and plus 1 minus x dm plus 1 dx m plus 1 operated on ln of x, and here due to this minus 1, this will be minus, and mc1, this will be again m factorial over 1 factorial times m minus 1 factorial, and dm dxm operated on ln of x, and plus n dm dxm operated on ln of x, and this equal to 0. Now you know m factorial can be written as m times m minus 1 factorial. So this factorial term, in this factorial term, m minus 1 factorial will cancel out and only m will remain here. Similarly here also only m will remain. So we can simplify this expression in this way. You can see this will be x dm plus 2 dxm plus 2 ln of x at is. So this is x dm plus 2 dxm plus 2 operated on ln of x, and all the terms containing the m plus 1th order differentiation will be now associated. So you can see here there is dm plus 1 dxm plus 1 and its coefficient, and in this here only m remains and here is 1 minus x. So we will associate these two terms, and this will be in fact m plus 1 minus x. This will be common, and then we will write the function. So this will be plus m plus 1 minus x and d m plus 1 dx m plus 1 operated on ln of x, and plus again see here, in fact dm dxm ln of x is present here and also in this term, So we can write it associating these two terms. This will be n minus m dm dxm operated on ln of x, and this will be equal to 0. Now let us put here, let ln m of x equal to dm dxm operated on ln of x. Let us consider that ln m of x equal to this much. So when we will use this assumption in this above equation, what will be your result? You can see easily. You can see then our result will be x d2 dx square ln m of x plus m plus 1 minus x d dx ln m of x plus n minus m ln m of x equal to 0. Let us say this is equation 3. Actually, in this equation, the constants n and m are positive integers, and this function ln m of x are known as associated Laguerre polynomials of degree n minus m, and this equation 3 itself is known as associated Laguerre differential equation. So you can say here the constants n and m are positive integers, and the function ln m of x are called associated Laguerre polynomials of degree n minus m, and equation 3 is known as associated Laguerre equation. So you can see we have defined the solution of this equation as ln m of x, and it has been defined in this manner, which is actually known as associated Laguerre polynomials. So now we will see the expression for associated Laguerre polynomials. The associated Laguerre polynomials. polynomials. As you have already seen, the associated Laguerre polynomials of degree n minus m is denoted by the symbol ln m of x, and this is defined as dm dxm ln of x. This is the basic equation which defines the associated Laguerre polynomials. But this equation or this definition is valid only when n is greater or equal to m. N is greater or equal to m. Now, you have already studied the Rodriguez formula for this ln of x. So, using the Rodriguez formula for ln of x, we can find the Rodriguez formula for ln m of x, that is associated Laguerre polynomials. Now, we know ln of x is defined as e raised to the power x dn dxn x raised to the power n e to the power minus x. You know this is known as Rodriguez formula for ln of x. So, using this expression for ln of x in the equation A, you may define lnm of x in an alternative manner, and that will be actually the Rodriguez formula for associated Laguerre polynomial. So, you can write lnm of x equal to dm dxm, and instead of ln of x we will write ex dn dxn xn e to the power minus x. Now you can see that this expression in RHS can be written as ex x raised to the power minus m and dn dxn e raised to the power minus x times x n plus m. So this, you can say that this is Rodriguez formula for associated Laguerre polynomial. So this is Rodriguez formula. Rodriguez formula. Now you have seen in the earlier lectures that all the special functions or all the polynomials are defined in terms of a series. So we will also define here the series expression for this associated Laguerre polynomials. So you can see the series expression for ln m of x is given as, in fact this is given as ln m of x equal to summation k0 to n minus m minus 1 raised to the power k plus m n factorial square over n minus m plus k factorial there will be minus here, n minus m minus k, not plus, factorial times m plus k factorial times k factorial into x raised to the power k. So this is the series expression for associated Laguerre polynomials. So you can see that we have defined the three expressions for the associated Laguerre polynomial. This is the basic definition, that if you have to find ln m of x, you must differentiate m times ln of x. This is the basic definition and most useful expression. Now, using either of these formula for ln m of x, we can find some of the values of the associated Laguerre differential equation. But before finding those values, I am giving you two important expressions or two important results here that will be very useful in evaluating the value of associated Laguerre polynomials. So you must remember, and also you can check these results. I am writing directly ln 0 of x. This will be simply ln of x, and its proof is obvious. You can see here that if m will be 0, then what does it mean? It means we are not going to differentiate ln of x. So when m will be 0, you can see the operator will be d0 dxm, which means 1. So ln 0 of x will be simply equal to ln of x. So this proof is obvious. Now another important result, you can see if n is equal to m, then the associated Laguerre polynomials are denoted by ln of x, and in fact this is simply equal to minus 1 raised to the power n factorial. So remember these two results, and then you can find easily the values of some of the associated Laguerre different polynomials. Now let us see some of the examples. First of all, L0 of x. You know this will be simply L0 of x using this property. This will be L0 of x. And you know L0 of x you have already studied. This is equal to 1. So this is 1. And if you use the basic expression here, you can see L0 of x will be equal to d0 dx0 L0 of x, and it means simply L0 of x, and that is equal to 1. You can see easily. Now let us find L10 of x. Again you can see using this property, the first property which I have defined here, this will be simply equal to L1 of x, and you know L1 of x is equal to 1 minus x. You have seen in the previous lecture. Again we will evaluate L11 of x, and now use this property ln of x equal to minus 1 raised to the power n times n factorial. So here this will be minus 1 raised to the power 1, because n is here 1, and times 1 factorial, and this will be simply minus 1. And you may also check it from the basic definition, that L11 of x you can write from the basic definition of ln m of x, this will be d dx L1 of x, and you know that L1 of x is what? This is 1 minus x, and so this will be minus 1. Now let us see the value of L2 0 of x. We will again use this property ln 0 of x equal to ln of x. So this will be simply L2 of x, and you have seen that L2 of x is what? This is x square minus 4x plus 2. In the similar manner, you can find the value of L2 1 of x. L2 1 of x. You can see L2 1 of x will be what? This will be d dx, from the basic definition, d dx L2 of x, and you know L2 of x is equal to this much, so this is d dx x square minus 4x plus 2, and after differentiation this will be actually equal to 2x minus 4. Similarly, you can find the value of L22 of x, and from the second property you can see that we can write it minus 1 raised to the power 2 times 2 factorial, and this will be simply equal to 2. You can also find it from the basic definition. So these are some of the values of the useful associated Laguerre polynomials. You may proceed in this way and find the higher order associated Laguerre polynomials.